Okay, any questions? Well, for every element, we can calculate quite a number of properties. I'm not so sure about the dielectric constant, but probably we can calculate the dielectric constant of every element. When it comes to molecule, things get more complicated. You mean by measuring their dielectric constant? Well, different materials can have almost the same dielectric constant, so you cannot separate them. And I mean, you can even create certain materials with a given dielectric constant by mixing various elements. So I don't think it will be practical. Other questions? About dielectrics, capacitors, connecting capacitors. Questions? Now let's look at what happens if we connect charged capacitors. So we have, let's say, one charged, one uncharged capacitor. If we connect them, what happens? Now this is not exactly electrostatics, because if you have a charged capacitor, let's say this is plus Q charge, this is minus Q charge, and it has a capacitance C1, and you connect it to another capacitor which has capacitance C2, initially neutral. Now, of course, some of the charges will just distribute itself. You see, in a conductor, when you reach electrostatics, we said that the potential is the same at every point on a conductor. So when we reach electrostatics in this configuration, the potential difference between these 2 points should be equal to the potential difference between these 2 points. But initially, at the moment that we make this connection, we see that there is no potential difference across here because the charge is 0, but there is a potential difference across these 2 points. So this is not an electrostatic system at this instant. But of course, if you wait long enough, eventually you will reach this configuration where here you would have a charge Q1, here you would have a charge minus Q1, and here you will have a charge plus Q2 and a minus Q2. So this will be the configuration, the distribution of the charges that you will obtain eventually. And since a conductor is an equipotential surface, every point on this plate, and on this wire are at the same potential. And saying every point on this plate, on this wire, and on this plate, it should also be on the same potential. So the potential difference across this capacitor, which is Q1 over C1, this should be equal to Q2 over C2. So if you just connect capacitors to each other, they will just distribute the total charge in proportion to their capacitance. So this is the ratio of the final charges. We also know that Q1 plus Q2 should be equal to Q. So you can determine what the final charge of each one of the capacitor is. Well, let's solve it in a different way. Plus Q1, plus Q2, no, minus Q1, minus Q2 plus Q2. I chose the signs wrong. So let's determine what Q2 is in this example. Now let's say this point is A, this point is B, this point is C, this point is D. What is the potential difference between A and B? That is VA minus VB. This has capacitance C1, this has capacitance C2. Q over C1. Now here comes the critical question. Is it positive or negative? Q1 over C2. True. Now does VA have a larger potential or a smaller potential? Well, the positive charges, they have a larger potential than the negative charges. So this is VA is larger than VB, so this is positive. Now let's look at VCD. This is VC minus VD. Well, this is also Q2 over C2. Now the critical thing is it positive or negative? Well, VD is where we identified as a positive plate, so it should be positive. No, VD is larger than VC, so this should be negative. But since VA should be equal to VC and VB is equal to VD, they are on the same conductor. VAB should be equal to VCD. So this tells me that Q1 over C1, this should be equal to minus Q2 over C2. So at least either Q1 or Q2, it should have the opposite sign. It should be negative. One of them should be negative, one of them should be positive. So even if I identified initially the positive and the negative plates wrongly, I mean, it doesn't really make any difference. I'm basically saying that if there is a charge on this plate, I will say that the capacitor has a positive charge. If there is a negative charge on this plate, I will say that the capacitor has a negative charge. Now, up to this point, whenever we were talking about the charge of the capacitor, we always defined it to be positive. But now, as in this example, it will start to be important. So it's like in a coordinate axis, you have to choose a positive direction and a negative direction. The same holds for a capacitor. You can choose a positive. What do you mean by the capacitor to be positively charged or negatively charged? You have to make a choice. It's independent. It's not important which choice you do, but once you make the choice, stick with it, and the sign of your final answer will tell you which plate is positively charged, which plate is negatively charged. Any questions on this one? Well, we calculated this problem. We have a parallel plate capacitor empty inside. What's the capacitance? A over L. A is the area of the plates. L is the separation of the plates. So if you imagine you put some charge Q plus Q and minus Q, we know that the potential energy stored in the system is equal to Q squared over 2C. And before we discuss what happens if you separate the plates, we have seen that you have to do work to separate the plates, and the work that you do goes into increasing the potential energy because the capacitance is now smaller. Just take the same parallel plate capacitor. but put a dielectric. What is the capacitance now? Well, let's say this is C0. This is K epsilon 0 A over L. And U0? No, not U0, U. This is equal to Q squared over 2C. U is equal to Q squared over 2C0 times the dielectric constant. U is equal to U0 over the dielectric constant, and the dielectric constant is always larger than 1, so this is less than U0. So we have these two cases let's just imagine we take this capacitor, we take our dielectric, and we move this dielectric, we put this dielectric in between these plates. Slowly. Well, the potential energy now decreased. What happened to the remaining energy? So energy should be conserved somehow. We are just imagining that we have these two plates, these two charged plates. Now we are just moving this insulator in between the plates, so the total energy of the system is reduced. What happened to it? So you are basically saying that the dipoles are beginning to be aligned, so that wastes some of the energy. Might be. What else? Or let's imagine that we create this dielectric such that the dipoles are fixed. Fixed to the final configuration. So will this change? Well, some of the work will go to aligning the dielectrics, I agree. But is that all? Okay. So that's why the potential energy changes, but where does it go? I mean, we always say that energy is conserved. So if energy of a system is changing, it has to go somewhere. Where did it go? The internal energy of the dielectric. So I'm just rephrasing my question. Let's say that in this configuration, the dipoles in my dielectric have some orientation, as your friend pointed out. They have some orientation. I fix their orientation. I have these magical powers to fix the orientation of dipoles in a given region. Okay? Then I have this configuration, and then I remove it. Remove the dielectric. I have the other configuration, or you can imagine I start from that one and just insert this one with the dipoles already oriented. So the internal configuration of my dielectric doesn't change. But still, nothing here assumes it anyway. I already gave you the answer, by the way. Yes.
So we have this capacitor we put there. Is this lost? Is this the question?
Yeah, we have this capacitor. We put the dielectric inside. The potential energy changes. What happens to the energy difference?
I think the charges.
In this one, well, the configuration of the charges in this final configuration on the plates is exactly equal to the configuration of the charges in the initial configuration. They are uniformly distributed. There's no heating. That's an effect we ignore. Nothing is heated up. Nothing is cooled down. The answer is exactly the same as our previous example when you are moving the plates. But this time we are not moving the plates.
To put the insulator between the plates, we did work.
Yes. Against what?
Against the electric fibers between the plates.
No, hold on. So if you are exerting a force on the dielectric, there are two cases. Either you are accelerating it, but that's not what we want. We are moving the dielectric with zero kinetic energy. So we are not accelerating it. If we are exerting a force and if it is not being accelerated, there is a force acting on the dielectric. So what causes that force? Electric field. Well, let's say we are just moving, let's say we are inserting the dielectric from the top. I'm pushing the dielectric downward. What will be the direction of the force that the electric field will exert? Which electric field is that? You see, if I have these two parallel plates, what's the direction of the electric field? I'm moving it this way, in the vertical direction. So how come there is a force on the dielectric which is in the vertical direction? Is the question clear? No. Or is the problem clear? So I say this is the problem. I have these parallel plates. One is positively charged, the other one is negatively charged. And I start inserting a dielectric. With almost zero speed. And we know that initially there is some potential energy. Initially, I mean, when the dielectric is not inside. And finally, when the dielectric is fully immersed, the potential energy is smaller. That is what we had argued over here. So this U0 is the potential energy of the dielectric when there is no dielectric, of the capacitor when there is no dielectric, and this U is the final kinetic energy when the dielectric is filled, when the capacitor is filled with the dielectric, which has, in this case, there is a smaller potential energy. Now here, I'm inserting the capacitor. Some of you got the correct answer that we have to exert a force on the dielectric. There is a force acting on the dielectric. So that we have to do some work. If we want to insert this dielectric with zero acceleration, we have to do some work on the dielectric. But now the problem is, what is the source of that force? And why the density will exert a force? The density of what? We are moving just imagine, this is the dielectric. I'm just slowly lowering it. There will be? Which density? Density of mass density, charge density. Okay, so how does that create a force in the vertical direction? So we need a force in the vertical direction. Do you all agree with that? Because I'm moving it in the vertical direction. If we want to have a force acting on it, if we want to do some work on it, we should be doing some work against some vertical force. Otherwise, if there's a horizontal force, we are not doing any work against that. Because the displacement is in the vertical direction. There's no gravity. We are in empty space, in vacuum. Self-induction? No, there is no self-induction. There is no magnetic field. We are in statics. Nothing is moving.
Well, earlier you said that, for example, if you have this kind of system and you have a body, the dielectric occupying the certain space of it, that is not everything, just part of it.
Okay.
Yeah. So in this case, too, at a particular time, the dielectric is only occupying just a part of it.
True.
Not everything. So it pulls, the charges pulls the electrons.
Which electron, which charges?
For example, when you explain earlier, if you have this, and then if
Do you agree that the electric field will be horizontal?
Yes.
If it's horizontal, it will create a force in the horizontal direction.
Yes, but the dielectric is occupying just a part of it.
Okay. Okay, so?
So in that case, the charge, that is the Q, it will be non-uniformly distributed.
Okay.
So if it is non-uniformly distributed, so it will be displaced to one part of it.
Okay.
So in that case, there will be a resultant force in the center.
Well, if there is a vertical component of the force, then there is a vertical component of the electric field. The electric field is no longer horizontal.
But it is only horizontal when we think of the plates as infinite. And when it comes to an end, we show that they bend.
Exactly. I mean, all of you got the correct answer. So there are these fringing effects. So you see, we said that the electric field close to the bends, they bend like this. So the electric field over here, they have a vertical component. So what will be the direction of the force exerted on the dielectric by the capacitor at this instant? So now there is these electric fields which are not horizontal anymore because it's not infinite. So what will be the direction of the force acting on the dielectric due to the capacitor?
Well, I'm thinking it should be downward, but I'm not using any of the electric field nodes. I'm just thinking about the potential energy difference.
Sure. We have to be consistent in our description. So the potential is decreasing. If we are lowering it, that means we are doing negative work since the potential is decreasing. For us to do a negative work, we have to exert an upward force to cancel this downward force acting on this capacitor. But then the question is, do we really understand how does this negative force come into is realized? So we said that we got the correct, almost there, we are almost there. We have said that there are these fringing effects on the boundaries, and hence the electric field is not uniformly horizontal. So the electric field over here have a upward component, the electric field here will have a downward component. Now, how do these create a downward force?
The electric charge side, that side is charged with negative.
Yes. So if this is the direction of the electric field, the polarization of the dielectric will be such that this part is slightly negatively charged, this part is slightly positively charged. So the force acting on the right will be in this direction, the force acting on the left will be on the other direction, and when you sum them up, you get this vertical force pointing downward. So a dielectric, if you are inserting it in a capacitor, it will feel a force which will basically pull the dielectric inside the capacitor, because that is the lower potential energy configuration. And in fact, by just measuring how the potential energy changes as you lower the dielectric, you can actually even calculate the force acting on the dielectric. The only thing you have to do is, let's say, this is the distance x, f that dx will be the work that you do. This should be equal to the change in the potential energy of the system. So this tells you what should be the magnitude of the force that you should exert, or what is being exerted on this dielectric by the capacitor. And this will, well, if you have any questions on this one, ask it now. This is part of your homework. To calculate that force.
Can you just say what you did last again?
The last one. This one. So you pointed out that as we are inserting the dielectric, the potential is dropping, because we should exert a force in the upward direction, and if the dielectric we inserted by a distance of dx more, the work that we do will be, let's say, minus f dot dx. This is the force that we exert. We are exerting an upward force. We lower the dielectric by an amount dx. So this is the work that we had done. But you said that the work that we do is what changes the potential energy, so this should be equal to the change in the potential energy of the system. But F us, this is the force that we are exerting, this is equal to F capacitor. This is the force that the capacitor is exerting, minus. So this is what we have. The work done by the capacitor itself is equal to the change in the potential energy. And if you just evaluate this U as a function of X, X being this distance, F is just du by dx. So you can actually calculate this force. And in this derivation, by the way, you don't need to take into account the fringing effects. It's enough that you assume that the electric field lines are horizontal to calculate this U. Still, the force that you calculate will be the correct one.
Consider a parallel plates. There's a dielectric inside in the middle. So, does the electric field lines bend?
You mean like this?
Yes.
The other outsides will be empty. Well, you still will have fringing effects even here. I mean, even if the plates are infinite, even if these ends go to infinity, the electric field lines in this region will not be uniform. They will bend slightly. Wait 2 more years. You will calculate this one. What do you mean? You have the capacitor, you have the dielectric, and bring the plates.
And one plate and bring the other plate.
Okay. So, what's the question?
Calculate that one.
Calculate the?
Okay, that's work.
Well, you can. I mean, you know the electric field, even if there is a dielectric. So you can calculate, if you know the electric field, you can calculate the work done. Of course, the presence of the dielectric will change the electric field, which will change the work done. Other questions? Do you understand the homework? No? Well, you see, this is the question. Our discussion, we agreed, yes, that if you are inserting a dielectric in a capacitor, the capacitor will exert a force on the dielectric. It will pull the dielectric inside. So there will be a force exerted on it. Now the next question is, what is the magnitude of this force? So that is your homework. Now the way to calculate it, I'm giving you the solution, is let's just assume that you insert it partially, such that only a length of x is inserted in the dielectric, in the capacitor. And let's just assume that you insert it slightly more. You increase x by dx. There is a force that you are exerting. This is the work that you do if you change x by dx. But this should be the change in the potential energy of the system. So the force that the capacitor exerts on the dielectric is nothing but the rate of change of U as a function of this x, defined over here. So the next task should be, what is U as a function of this x? Well, that is also you can do. Just imagine this is just 2 separate capacitors, one of size x, the other one of size the total length minus x, or the total area minus x. When you know the capacitance of this one, you know the capacitance of this one. Of course, the charge you have the charge density over here and the charge density over here will be slightly different. So you can calculate the total energy stored here, the total energy stored here. The sum is just your U. Or we have already solved the problem of a capacitor which is partially filled with a dielectric. Well, in that example, we had half of the area was filled, but you have to generalize it to this case. So you know the capacitance of the system. You know the total charge. You know the total charge. You know the total capacitance as a function of x. That means you know U as a function of x. If you know U as a function of x, you can calculate the force that the capacitor exerts on the dielectric.
Yeah, so many parallel resistors, we are changing them one by one. Dielectric.
Well, rather than so many, I would just divide it into 2. That should be enough. Other questions?
Sorunun başında o dipolların finaldeki olacağını fix olduğunu söylediniz.
Well, we are assuming that the internal energy of the dielectric doesn't change during this process.
Aslında diğer elektrik field'ın yönüne ters bir elektrik field aslında içeriye doğru negatif bir iş yapmış olmayacak mıyız aslında?
Why should we?
Yani o da aslında potansiyeller düşünüyor.
Well, you see, of course, when you are evaluating the potential energy, the dielectric itself also has a potential energy due to, as you said, the electric field created by the dipoles in the dielectric. But that energy is not something we can extract. So for us, it's not really relevant. Other questions? Okay, so let's just do one more question. So this is the question. We have this combined capacitors. We connect it to a battery. Well, the battery just makes sure that this point and this point, the potential difference between these 2 points is V. That is what the battery does. It is fixed. What is the charge that moves in my system? So this will be, let's say, this will be negatively charged. Eventually, this is negative, this is positive. This will be negatively charged. These plates will be positively charged. This will be positively charged. What is the charge in this plate? So that's basically the question. And let's just, everything is the same, C, C, C. Now I'm saying that, what is the charge in this capacitor? That's the question. Okay, so what's that? So let's just say that this is Q. This is minus Q, so this will be plus Q. Well, if this is plus Q, these will be minus Q and minus Q. And minus Q over 2, sorry. And plus Q over 2, plus Q over 2. Do you agree? Now let's see, what is the potential difference across this capacitor? Q over C. Now the potential difference across this capacitor, well, the charge is Q over 2 over C. So the total potential difference between these 2 points will be just Q over C plus Q over 2C. The potential difference between this point and this point is the same as the potential difference across this capacitor. And the potential difference between this point and this point is the sum of the potential differences between across this capacitor plus across this capacitor. It's Q over C plus Q over 2C. But we also know that the battery keeps the potential difference between this point and that point at the fixed value of V. And so you can just determine the capacitance, the Q. Well, I didn't even calculate the equivalent capacitances.
Last example, if we have a battery that keeps the potential difference constant.
Which one? In this one?
The potential decreases the absence of a battery. What if we have a battery that keeps the potential difference constant?
So here we were discussing the force acting on the dielectric, and we assume that the charge is constant. Now your friend is asking this question. Let us assume that we connect this capacitor to a battery, so that the battery keeps the potential across the potential difference between these 2 plates constant. Then what happens? Well, that will be your homework question in 1 or 2 more homeworks. But before that, it will be your homework after the exam. So after we study some circuits, some more properties of the batteries. Any last minute questions? Okay, see you after the weekend.